Welcome! In this elementary calculus tutorial, we are going to introduce you to differential equations. And so we will be solving some very basic differential equations, and it looks to me like all of these are going to be separable equations and some initial value problems towards the end. Okay, so stay tuned. Let's get into it. Now, our first question asks us to solve dy on dx plus 2xy is 0, and really verify whether y equals e to the minus x squared is a solution to that, or if it's just some particular solution. So let's solve this. Now, we want to separate this. This one is a separable equation, so we want to take the 2xy over to the right-hand side and put dy on dx equals minus 2xy, and then we can pretend for a moment that this is a fraction, this dy on dx, and take the dx over to the right hand side. But as soon as we do, we'll put an integral on these, and so we want to also divide by the y, so the y goes with the y's and the x goes with the x. Okay, so let's go ahead and do that. Dy over y is minus 2x dx. Now you can see I've performed what looks like an algebraic trick, treating this as a fraction, although it's not. And then as soon as we do, we put an integral sign on this. Now, rather than me put the integral here, since this is a constant, this constant can come through, and so I'll put the integral sign there. All right, now let's integrate both sides. So on the left, the integral of y to the minus 1 with respect to y is the natural log of y. And then over here, the integral of x with respect to x is a half x squared. So we have this equal to minus 2 times a half x squared. And then we need a plus c. Okay, so simplifying this, the right-hand side is minus x squared plus c. This is the natural log of y. Now we want to express this, if we can, as a function of x. In other words, y is a function of x. But to do that, we need to, or e to the power of, is what I mean to say, e to the power of minus x squared plus c is our y. So y equals e to the minus x squared plus c. Now what this is e to the minus x squared times e to the c. Because remember, when we have the same base, we can add the exponents and get this. So we can do that in reverse also. Now, e to the power of c is a constant, so let's call that constant a. And so then we will write y equals a e to the minus x squared. Okay, let's have a look at our question. The question says determine whether y equals e to the minus x squared is the general solution to that equation, or is it just a particular solution? Well, the answer is that it's just a particular solution. So I'll write that here. Y equals minus x squared e to the x, y equals e to the minus x squared is a particular solution only, and not the general solution. Okay, let's move on to question 2. Y dash times natural log of x minus y on x equals 0. Is y equals c, natural log of x, the general solution, or is it just a particular solution? So to find out, let's just solve this equation. Now this one will be separable also. Let's write y dash as dy on dx. And let's, well, for now, I'll just rewrite that. Okay. I'll take this over to the right-hand side. And now let's put the dx on the right-hand side, and we'll divide both sides by natural log of x and divide both sides by y also. So then we will get dy over y equals 1 on x. Then we'll get a dx, but what do we do with this natural log of x? Well, we divide both sides by that, so that'll end up down in the denominator with the x. So we have this, and then we put our integral signs on this and proceed to integrate. So we want to do this one by substitution or use substitution. So on the side, I will just say let u be equal to the natural log of x, and then I differentiate this so that du on dx is the derivative of natural log of x, which is 1 on x. And then I want to rearrange this so that I can see how to replace dx, pretending like it's a fraction. Of course it's not. So dx, I'll replace this via substitution with x du. So I've taken the x over to this side, taken the dx over to this side, and that just tells me what replacement I want to make in here. Okay, so coming back to our integral, we have 1 over x u, and then we're replacing dx with x du. And so we get the integral of u to the minus 1 with respect to u, which is the natural log of u plus c. But u is the natural log of x. So then we have natural log of x plus c. And over on the left-hand side, we have the natural log of y. Okay, then this is fairly easy to finish off. So now what we have is y equals e to the power of the natural log of x, and then plus c. So we have then e to the power of c, e to the power of natural log, which is natural log of x. And so we can call this e to the power of c, just for the sake of the question, let's call that c1. So c1 natural log of x. Okay, and so we've solved that equation. So we see then that y equals c natural log of x is the general solution. All right, let's move on to question 3. Okay, so question 3 says, solve the differential equation dp on dx is the square root of p over x. All right, now we can break this up. We don't want to square both sides. We can break it up and write dp on dx is p to the power of a half over x to the power of a half. Now let's pair the x with the x and the p with the p. So when we do that, we have dp over p to the half, which we can write as p to the minus a half in front. And then this x to the 1/2, we can bring it upstairs to the numerator and call that x to the minus a half in the numerator. So x to the minus a half dx. And then we put our integral signs on and we integrate both sides. Now, since minus a half is not minus 1, we add 1 to the exponent. And divide by the new exponent. We can see that exponent there will be a half, so we divide by 1/2. We need a plus c. Now, same story on the left-hand side. We will have 1 on 1/2, p to the power of minus a half plus 1. Now, let's simplify these. So 1 over 1/2 is 2. So we have 2p to the power of plus 1/2 is equal to 2x to the power of plus 1/2, and then plus c. Okay, so we might want to have p as a function of x. So let's divide throughout by 2 and then square both sides. So p to the 1/2 is equal to x to the 1/2 plus 2c, but let's just call that a. Okay, and so now we want to square both sides. So we have p is the square of x to the 1/2 plus a. And this incidentally is the square root of x plus a all squared. All right, now what was the question asking us? Just solve it. Okay, we've done that. So here is the solution to that equation. Let's move on to question 4. So in question 4, we are asked to solve this differential equation. It's also separable. So we want to take the x cubed over to the right-hand side and bring the dx there as well. So we'll write dy, or y squared dy, equals minus x cubed dx, and then put the integral signs on. And we need to integrate this now. So we add 1 to the exponent of the y. So y to the power of 3, divide by the new exponent. Now I'm leaving off the plus c on this side because I only need one c in the equation. So I'll put it on the right-hand side. Now adding 1 to this exponent of 3, we get 4. So minus 1/4 x to the power of 4, and then plus c. All right, so we should tidy this up. But notice that we're not going to be able to get a nice function of x for y because we have a cube, so which would give us 3 complex solutions. So I would prefer to go with a nice looking curve in this case. And so let's multiply both sides by 12. So then we'll get 4y cubed equals minus 3x to the 4th plus some other c, which I'll call a here. Okay, now I'll add both sides, add minus 3x to the 4th to both sides. So 3x to the 4th plus 4y cubed equals a. And I'm fairly happy with that solution. So let's move on. But first, I want to show you something I grabbed out of the Mathematica help file. This just solves a differential equation for you. So let's try it with this one. Now, dy on dx is y dash. So I'll put y squared next to that. And then we'll put plus x to the power of 3 equals 0. And let's see what Mathematica gives us there. So it just spits it back out. All right, now just for the sake of it, let's go back to one of our previous questions. Say question 1. All right, let's try this with question 1. So dy on dx plus 2xy is 0. What? It appears with no arguments. Okay, is that the issue? Oh, right, because I have forgotten yeah, maybe that was the problem in the other. Okay, so there we go. Now we get a solution. We get an answer to question 1. So let's go back now and try again with this question 4. And then we're adding x to the power of 3. Okay, so it gives us a solution. It gives us 3 solutions, but you can see some of those involve complex numbers or non-real numbers. So minus 1 to the power of 2/3. Okay, so you can get something meaningful from this. Like, for example, I could just take this third one and do some algebra on that and form this curve. I'll just show you now, because I can, what this curve might look like. So 3x to the power of 4 plus 4y to the power of 3. And I'll just choose a constant here, like 2. All right, so I will write contour plot. And then when I do that, I need to specify a range of values for the x and a range of values for the y. Okay, let's run that. It'll take a little moment. Okay, and it gives me something that looks a little bit like an elliptic curve. Anyhow, all right, let's move on to question 5. I'll scroll that so you can see it. Okay, now in question 5, we're asked to solve the differential equation y plus t dy on dt is 3ty. Now I'm guessing that this is separable, so let's make it look like it's more separable. So let's take the y over to the right-hand side. So we have t dy on dt equals 3ty minus y, but incidentally, we can factorize the y out of this and call this y outside of 3t minus 1. Okay, so now it's clear how we should separate this. We should put the t's with the t's and the y's with the y's by dividing both sides by the y and taking all the t's over to the right-hand side. So then we'll get dy on y is 3t minus 1 all over t dt. Put on our integral signs. And now we can simplify this right-hand side and call this 3 dt. I'm just dividing this t into both of those terms in the numerator. And then we have minus t to the minus 1. Okay, so now we can integrate both sides easily. So on the right-hand side, we have 3t, and then on the left-hand side, we have minus the natural log of t and plus c. Okay, on the left-hand side, we have the natural log of y. Okay, so now we can write y as a function of t rather easily. So y is equal to e to the power of 3t minus natural log of t plus c, but let's simplify this somewhat. So y is equal to e to the 3t times e to the c, but e to the c we can call a. Now e to the natural log of t is just t, but we have a minus there. So that would invert this so that we would have 1 on t there, but also we can take this minus 1, put it up into the exponent of the t here. And so now it becomes perhaps even clearer, so that this part of it is e to the power of the natural log of t to the minus 1. And so we get t to the minus 1 or 1 on t for that. Okay, let's check this with Mathematica. So I'll come back up and I'll write in our differential equation. So we have y plus t times dy on dt. So I need to change this and write this in terms of t. And then this is equal to 3ty as a function of x. Oh, no, as a function of t, isn't it? And then that's y of t, and this is t. Okay, let's try that. So it gives us exactly what we've got. The c bracket 1 is just a constant there. Okay, let's move on to question 6. So question 6, solve the differential equation e to the 2x dy on dx plus e to the x is 4. All right, so let's see, what can we do here? We'll take that e to the x over to the right-hand side. So we have e to the 2x dy on dx equals 4 minus e to the x. Okay, now we want to divide throughout by e to the 2x. And so we'll get dy is 4 minus e to the x all over e to the 2x dx. Put our integral signs on these. Now we can simplify the right-hand side a little bit before we integrate, so we should do that. The left-hand side is really easy to integrate. We just get y. And then on the left, let's put 4e to the minus 2x minus e to the minus x. We're just adding the exponents. This will be x minus 2x in the exponent there, which is minus x in the exponent. Okay, so now we can integrate this. So remember, if I were to differentiate e to the minus 2x, I would bring down a minus 2x using the chain rule. So here, if I'm going the other way, I want to divide by minus 2x. So 4 over divide by minus 2, that is. So 4 over minus 2, e to the minus 2x. And then over here, we have plus e to the minus x plus c. Now, just check, if you were to differentiate these, do you get what's inside? Well, yes, you do. Okay, so that tells me that's correct. Now, let's just simplify it. So it says y equals minus 2 e to the minus 2x plus e to the minus x plus c. All right, that's question 6 done. Let's do question 7. ds on dt is sec of s, and s of 0 is 0. So this is an initial value problem. When you have an initial value like this, so this says when t is 0, s is 0, but you can also write it as a function, which is sometimes more convenient. All right, so let's solve this equation first, and then we'll deal with the initial value. And you use the initial value to get the plus c, or the c value. All right, so ds over sec of s is dt. All right, so we've separated it, put our integral signs on. So that's easy to do. Now, 1 over sec of s is cos of s. So we have the integral of cos of s ds is the integral of 1 dt. Okay, fantastic. So now that we have that, let's integrate this. So the integral of cos is sine. We have sine of s. Now on the right-hand side, we have t plus c. Okay, now you can get s as a function of t by taking the inverse function, right? Provided that's in a range that's valid. Now let's sub in t is 0 and s is 0. So sine of 0 is equal to 0 plus c. Okay, now sine of 0 is 0. So 0 is equal to c, and so that says c is equal to 0. So then we get sine of s is equal to t. And so if we want to get s as a function of t, well, then we apply the inverse sine function, or arc sine, to both sides. So s is equal to arc sine of t. And sometimes people write this as sine superscript minus 1 for the inverse function. But this is more calculator speak. So I'll just say in brackets on calculator. I prefer this because with this arc sine, there's no confusion between that and 1 on sine, right? There's no confusion whatsoever. Okay, question 8. Solve the initial value problem. Y squared, hang on, is that 8? 2x dy on dx equals y natural log of x. All right, so we want to separate this since it's separable. So we've got dy on y natural log of y is equal to 1 on 2x, but I'll write this 1 over 2 x to the minus 1 dx, and we'll put our integral signs on. Now this looks a little bit familiar. Didn't we do something like this in question 1 or 2? I don't know. You tell me in the comments. Okay, so now I'm going to let, yeah, that's right. We're going to get a log. Okay, so let u equal natural log of y. We differentiate and take du on dy, and so we get, what do we get? We get 1 on y for that derivative. Okay, then we do our algebraic trick and say that we're going to replace dy with y du. All right, so let's do that here on the left-hand side. So we have y du over y u. Now integrating the right-hand side is easy because the integral of x to the minus 1, since that's an exponent of minus 1, that gives us the natural log. So we have 1/2 natural log of x and then plus c. Okay, so now on the left-hand side, we can keep going with this integral by substitution. So we've got the integral of u to the minus 1 du equals 1/2 natural log of x plus c. And so the integral of u to the minus 1 with respect to u is the natural log of u. But u, remember, is natural log of y. So we have ln of y. Okay, and so we want to solve for y if we can. So natural log of y is a e to the 1/2 ln x. The plus c is in the a. Okay, and then y is equal to b, or e to the power of a, let's call it b, e to the power of e to the power of 1/2 natural log of x. Okay, and there we go. Okay, so we can simplify this considerably. So the right-hand side, we can write this as b e to the power of e to the power of natural log of x all to the power of 1/2. Remember, you can multiply the exponents. When you have something like this, I can bring this and take the product of 1/2 natural log of x, and that's what we have there, so I can do that in reverse. Now, e to the power of natural log of x is just x, so this is b e to the x to the power of 1/2, or e to the square root of x, and that's our y. All right, so now we are ready to use this initial value. When x is 2, y is equal to e. So that says e is equal to b e to the power of the square root of 2. So then, dividing both sides by e to the power of the square root of 2, b is equal to e to the power of 1 minus the square root of 2. And so then we have y is equal to e to the power of 1 minus root 2 plus the square root of x. All right, so question 9, we've got an initial value problem, y squared e to the x plus e to the minus x times dy and dx is y squared, where y of 0 is 2. Okay, now we want to take the y squared e to the x over, don't we? I think so. So e to the minus x dy on dx equals y squared minus y squared e to the x. So we can factorize out the y squared on the right-hand side and call this y squared 1 minus e to the x. And so next, we can multiply both sides by e to the x and divide by y squared. So we'll get dy on y squared, or y to the minus 2. And then on the right-hand side, we will have 1 minus e to the x. And then we are multiplying this by e to the x. Take this over, and then we have dx. Okay, I think that looks good to me. Yeah? Does it look good to you? Okay. Let's put our integral signs on. And now we want to expand probably the right-hand side and then integrate. So the left-hand side is easy to integrate. All right, we add 1 to the exponent. We get y to the minus 1. Divide by the new exponent, which puts a minus 1 there. Now on the right-hand side, we'll write this as e to the x minus e to the x times e to the x is e to the 2x. Okay, and now we're ready to integrate that right-hand side. So the integral of e to the x is e to the x. The integral of minus e to the 2x is minus 1/2 e to the 2x. Then we have our plus c. Now let's express the left-hand side as minus 1 over y. So it's clear we need to multiply throughout by minus 1 and then invert both sides. Okay, so let's do that. So y is equal to 1 over, now I'm also multiplying this by minus 1. So when I write this on my denominator, I'm multiplying by minus 1 as well. So 1/2 e to the 2x minus e to the x, and then plus some other constant, let's call it a. Okay, and there we have our general solution, but now let's use our initial value. Y of 0 is 2. So 2 is equal to 1 over 1/2 e to the 0 minus e to the 0 plus a. So e to the 0 is 1. So then we have 1 over 1/2 minus 1 is minus 1/2. So a minus 1/2 is 2. All right, so let's invert both sides. And so we get a minus 1/2 is equal to 1/2. So in other words, what I'm doing here is multiplying both sides by a minus 1/2 and then multiplying both sides by 1/2 to get this. All right, so let's add 1/2 to both sides, and so we get a equals 1, or 1/2 plus 1/2 is 1. All right, so now that we have that, and we get our solution, y equals 1 over 1/2 e to the 2x minus e to the x plus 1. Okay, question 10. 2y cos y minus sine of y, all in brackets, times dy on dx equals y sine y, where y of 0 is pi on 2. All right, so we want to take all of these y's over to the right-hand side. Or actually, no, we want to take the y sine y to the left-hand side, dividing both sides by that. Okay, that 2y cos of y minus sine of y all over y sine y dy equals dx. Put the integral signs on. And we need to simplify the left-hand side before we calculate that integral. Okay, so in the first term, let's write this carefully for you. So we have 2 cos y over sine y. And so what I'm doing here is dividing or canceling the y's in this term here. So this I'm dividing by this term and this second term. So when we do that on the first, we can cancel the y, but when we do this on the minus sine y, we cannot cancel the y. We can cancel the sine y. We have minus y to the minus 1 for that piece of it. Okay, now the integral of 1 with respect to x is x, and now we need a plus c somewhere. Okay, now let's break this up into two integrals. So for this one, we're going to want to substitute, letting u equal sine y. Now this one here is very easy. So let's write 2 times the integral of cos of y over sine of y. And the reason I know that I should let u equal sine of y is because if I differentiate sine, I get cos. In other words, the derivative of the denominator is the numerator, or a constant times it. And so a substitution letting u equal that denominator will work out nicely. All right, so let's finish writing that line. So minus natural log of y equals x plus c. All right, so let's let u be equal to sine of y. We take du on dy. So I'm trying to make that look like a u. Okay, so the derivative of sine of y with respect to y is cos of y. Now we need to take the dy over, divide by the cos, and we'll see how we should replace dy. dy gets replaced with du over cos of y. So let's come back over here and finish this off. So we have 2 cos of y over u. Now we're replacing dy with du, over cos of y minus natural log of y is x plus c. All right, sorry about the messy writing. Let's keep going. So this integral right here, we can cancel the cos y's, and so we just have the integral of u to the minus 1 du, which is natural log of u. And so we've done the integrals, but we need to put back in the sign. And so the 2 can also come up into the exponent. So let's write this natural log of sine squared of y minus natural log of y equals x plus c. Okay, so let's pack those 2 natural logs together, because the difference of 2 natural logs, or the difference of 2 logs, is the log of the quotient. So natural log of the quotient of those 2, sine squared y over y, and so this is x plus c. Okay, now it's not practical to write y as a function of x here, so what we'll do instead is we'll let these be exponents to base e, and so we'll write sine squared of y over y is equal to a e to the power of x. Okay, so what I've done on the right-hand side is we just have e to the power of x plus c, but then that's e to the x times e to the c, and e to the c, we're going to call that a. Okay, so now let's use our initial value, y of 0 is pi on 2, but I'm out of paper on this sheet anyway, so I'll grab another page. Okay, and so we'll write sine squared of y over y is a e to the x, where y of 0 is pi on 2. So in other words, when x is 0, y is pi on 2. So then we have sine squared of pi on 2 over pi on 2 in brackets is equal to a e to the power of 0. Now, of course, e to the power of 0 is 1, so the right-hand side is just a. All right, now sine of pi on 2 is equal to 1. All right, so this is 1 squared is 1. So 1 over pi on 2 is equal to a. And so multiplying top and bottom of this left-hand side by 2, we see that a is equal to 2 over pi. And so now we can go back and find our solution that we put here, and we can sub in the a value. So sine squared of y equals 2 on pi, e to the x, and then times y. So I've taken the y and put it over on the right-hand side just to beautify this. And we're done.